Hello everyone. In this presentation, we'll see the proof for the theorem that L infinity is not separable. So before we see the proof, let me clarify the terminology we are using. L infinity stands for the set of all real or complex sequences which are bounded. And this set forms a metric space with the supremum metric which is defined as follows. And finally, separability means that a set X is said to be separable if it contains a subset A which is both dense and countable. So for example, R is separable because R contains a subset Q or rational numbers which are dense in R as well as countable. So now let's look at the proof why L infinity is not separable. We shall prove this by contradiction. So assume on the contrary it is separable. Then what does happen? It then means that there is a subset A of L infinity which is both dense and countable. So now choose epsilon to be 1 by 3 and we claim that we can write L infinity as a union of all these open balls of radius 1 by 3 around each point of the dense set A. This is indeed true because of the following fact we are given or assumed that A is dense. So if A is dense and you take any point in capital X, X turns out to be an accumulation point of A because the closure of A gives you L infinity. Now since X is an accumulation point of capital A, it means that however small neighborhood you take around X, you can always find some point in capital A, I'm calling it small a here, such that A belongs to that small neighborhood. Now if A belongs to this open ball of radius epsilon around X, it means that the distance between X and A is less than epsilon. Now since D is a metric and metric satisfies symmetric property, D of A comma X will also be same, which is less than epsilon. Then this implies that if you take an open ball of radius epsilon around A, X should also belong to that because distance between A and X is also less than epsilon. So what we essentially showed is that given A is dense, what happens is any point in capital X, you can always find a point A in capital A such that irrespective of the epsilon again, X is contained in an open ball around a point A in capital A. So if I take all such balls, so for every point small a in capital A, if I start taking these open balls of some epsilon radius, then every X in capital X should belong to one of these. So that's exactly what we are claiming here. Just that we have chosen epsilon to be 1 by 3 here, and here we showed that epsilon can be arbitrary. There is no restriction on epsilon, and therefore we can always choose any particular value. In here we have chosen 1 by 3. So moving ahead, now define B to be the set of all sequences such that the sequence are made up of 0 or 1. Then the following statements are true about B, which is that B is firstly subset of L infinity. Okay, we'll see why is this. This is because let's first understand what L infinity is. Basically, L infinity contains all the sequences which are bounded. So which means to show B is a subset of L infinity, it's enough if I show that every sequence in B is bounded. And that is actually true because every sequence in B just has these values 0 or 1, which is bounded by the values of 0 and 1 itself. Therefore, B is bounded, and since L infinity contains real or complex sequences which are bounded, B has to be a subset of L infinity. And the second point is B is uncountable, and the proof of which I have skipped in this presentation because I wanted it to be a bit smaller. So but it's not hard to see check that B is uncountable. The proof is pretty elementary in nature. And finally, L infinity we have seen has a supremum metric. So what happens if I restrict that metric to the set B alone? That is, if I take the sequences xi n and eta n from B2 sequences, then what can be the distance between these two? So it is easy to see that it will be 0 if both are equal, and even if they differ at one point, the supremum metric would give it to be 1. So therefore, the supremum metric which is defined on this L infinity turns out to be a discrete metric when restricted only to this set B. So now again recall what we have just showed in previous slides, that is L infinity can be written as this union on the right hand side. So firstly we had here that B is a subset of L infinity, and L infinity can be written as a union of open balls around each point A. Then we can conclude that B is a subset of this union. Now you take any x that belongs to B. Now since B is a subset of this entire union here, B has to belong to this union. In particular, if it belongs to union, it has to belong to one particular open ball, isn't it? So I'm calling that open ball to be B1 by 3 of A naught, for some A naught belong to capital A. Then we see that if you take any other point y in B which is not x, then let's look at this discrete metric. We have a y which is not x, which means its value, the distance between y and x cannot be 0 because we are already given that those two y and x are not equal, which means that it has to be 1. So since its distance is 1, it cannot fall within the this ball, because if y belongs to this ball, it means that the distance between x and y is less than 1 and it's not equal to 0, so it will start giving you a contradiction. So from here we concluded the important main statement that we are looking for here is, if there is a particular value x that belongs to one of these sets in this union, then you cannot have another point y which is not x such that y also belongs to the same set. So this actually leads us to the contradiction, which I would like to frame it as follows. So we had B is uncountable, and we also had this subset relation. Now we have that A is countable, okay, and we are taking the union over all small a's which belong to capital A, which means this is a countable union. Now B is uncountable, so we cannot have each one of these sets to be countable and B to be uncountable, because if each one of these sets B 1 by 3 of A was countable, it means that countable union of countable sets is countable, then this entire union would become countable. But then you would have an uncountable set contained in a countable set, which is a contradiction. So we conclude that at least one of these sets B 1 by 3 of A must actually have uncountable number of points of B. But then this is again not possible, because we just showed that at first place, if there is one point that of B that belongs to a particular set B 1 by 3 of A, say, you cannot have a distinct point Y which is not equal to X to belong to the same set. So if there you cannot have 2 points itself in the same set, you can forget about asking uncountable number of points of B to be in the same set. So this leads us to the contradiction, and therefore L infinity is not separable.